So if you take a look at the capacitor or at the output voltage Vout, when the capacitor is charging and discharging, how the response at the output part or output load terminal. Okay, by right the average output should be stabilized at this expected voltage level, but ideally, or this is ideal, but practically there will be a swing in terms of ripple, delta Vout here, minimum and maximum. Okay, what happens that during a positive, so we assume that the capacitor is very large, such that it can maintain the ripple at very minimum range. So what happens that when the current is at positive means that it absorbs, it delivers into the capacitor, it goes into the capacitor. So when it goes to the capacitor, it ramps up from minimum to 0, minimum until the capacitor is fully charged, and it ramps up to 0, means that comes in until the capacitor is full. So means that instead of deliver to the load, it goes into the capacitor, so the voltage will at the load point will reduce gradually. But when it full charge, it starts to deliver out. So means that it deliver out, so means that your output will start to ramp up. So it delivers out and it reduce, so it ramp up and start to reduce again. So at this level, it absorbs. Is that just now it delivers, now it absorbs again. So what happens is that the output voltage will start to reduce again, absorb and start. This is the cross line of delivering, absorbing, deliver, absorb. So what happens that during your crossing line of deliver and absorb, so the peak of minimum and maximum happen. Maximum voltage at the output, so minimum voltage at the output. So during the capacitor is absorbing, you will see that your output will be at minimum. When it starts to deliver, it ramp up, but it ends here. It ends at the crossing point, and crossing point of your deliver and absorb. Deliver and absorbing. Okay. So the amount of minimum and maximum magnitude here is considered as delta Vout. So the output voltage ripple is equal to delta Vout divided by Vout. How much the ripple divided by the average Vout here. So that is the output voltage ripple. So it's stated that when the capacitor current is positive, the capacitor is charging. When it's ramp up, the capacitor is charging. So you can see that the voltage at the output point or terminal will be reduced because it charged the capacitor. So the output ripple voltage is defined as a fraction of the output voltage, and the value capacitance considered as delta Q equal to how much the duration times the amount of changes of your load current, inductor current, divided by 8, because we can see here this is the amount of one cycle, and from minimum back to minimum is one cycle. So the delta Q happen during half cycle. So half of it, and half of half cycle is 1 divided by 8. Okay, so delta V naught equal to total time of the changes of inductor current divided by 8. So because Q equal to CV naught and CV out. Okay, you can see that when you solve the equation, you can see the equation solution or the equation details in the textbook. page 204, if I'm not mistaken. So means that we are able to calculate how much the value of C, so that we are at certain amount of what level of voltage ripple that we expected. So we can determine how big the C capacitor value that we need to assign or allocate at the circuit. So we decide in terms of how much our duty cycle we want to use in terms of the range. So we can determine how big the capacitor we should put in to get certain value of voltage ripple that we expect. So this is the parameter that involved in terms of frequency, duty cycle. So the main things that how much ripple we expect, we can adjust accordingly in terms of the parameters, in terms of their frequency, duty cycle, and the C value. So we can take a look at the example later. Now we discuss on the buck step down discontinuous mode. Just now is the CCM, now DCM. So what mean by the DCM is that the average inductor voltage and also average capacitor current, inductor voltage VL here, and also the capacitor current are 0 for periodic operation. So in terms of just now, we can see that the in CCM, the positive cycle is positive, then negative cycle is negative, then it return back to positive. We have only 2 levels, but now we have 3 levels: positive, negative, 0, return back to positive, negative, 0. Means that it has some range of 0 voltage on the inductor, and on the capacitor, in terms of the current, we have 0 gap for some periodic operation. Means that the capacitor and the inductor current, the value are the same, but shifted a little bit in terms of their magnitude. You can see that it ramps up, then when we take out the switch off, it ramps down, but after that it goes to 0, and not going back to the negative, but it goes to 0, and it start to ramp up again after a certain period, after it start new cycles, down and 0. So it means that it has 0 or blank period in between before it starts next cycle. So the formula is that Vs minus V naught times duty cycle of the whole period minus V naught dt equal to 0. The amount of this one minus this one equal to 0. So we have here V naught divided by Vs equal to D plus D1. This is D1. Duty cycle for the positive period, duty cycle for the ramp down, switch off, and we have 3 duty cycle here. Duty cycle for the blank period. So this is the amount of IL. This is the Imax. So how to find Imax in terms of the inductor current maximum? So the change in current over the time when switch is closed. When the switch is closed, or when the circuit is switched on, the analysis determines that when with the duty ratio of D1 just now, D1, you will get your IL max of delta IL of V naught D1 times period of T here, the whole cycle of ramp up, ramp down, and blank, so T divided by L. So when you substitute in this with this half of IL max here, you will get V naught or V out equal to V source D divided by D plus D1. So D plus D1. So D plus D1 here will determine D divided by D plus D1 here will determine times Vs the V out. Just now for CCM, Vs times D, but for DCM, the output is equal to V source times D divided by D plus D1. D plus D1 here. So this is the amount or the value that affect in terms of the how much the output voltage, in terms of how much we want to set. So the duty cycle of D1 and D will take place. Okay, design consideration for DC-DC converter. So as I told you before, we can change in terms of their switching frequency, the parameters that can be changed, their inductance value, their capacitor value, such that the output voltage ripple can be set at minimum ripple. So it means that the output voltage and the output current should be continuous and at minimum ripple. So it should be smooth in terms of output and current. So but when we increase frequency, we can minimize in terms of inductance value and also the capacitor value. As we can see, if F is increased, means that your C will decrease. Same goes to the when we increase L, and if we increase F, the L also should be can be decreased. And so the smaller the component, the cheaper it could be, means that the more profit you can get from your product or your design. But there is some limitation. When you increase frequency at higher frequency, there will be a higher switching losses on the switch. And so with higher switching losses, so it means that you have to manage, or you have to dissipate the heat. So losses means that it will convert into heat, so it will degrade in terms of the overall efficiency of your converter. So means that you might have to acquire larger heat sink to your switch. So it might occur some extra cost to your design. So typically, if you operate above 20 kHz, should be operate above 20 kHz, because below 20 kHz there will be audible noise. But you cannot. There is some limitation, 20 kHz, and cannot exceed some certain limit, because at about 50 kHz and above there will be significant in terms of losses. 1 MHz is preferable for communication, but for power conversion should be around 20 up to 50 kHz. Lower frequency should be avoided to avoid in terms of audible noise. Higher frequency should be avoided to reduce in terms of switching losses. In terms of inductance, should be larger than L minimum, because if you reduce more than lesser than L minimum, you will enter DCM. So it should be larger. In some design, you should select or consider 25% larger than L min. So other kind of inductor selection should be, example, at 40% of the average inductor current. So switches, example MOSFET, IGBT, and so on, must be able to withstand maximum voltage stress and also the maximum current, maybe in RMS or average, depends on the datasheet. So if you exceed the current, so you should consider the heatsink, because you cannot exceed in terms of temperature rating. We shall see in terms of heat management data on this converter. So to recall, you can read all down the statement.